Welcome to the Explainer. Today, we're looking at something you rely on literally every single day, but you probably never truly think about. We are zooming in, way in, to uncover the explosive, microscopic reality of everyday manufacturing. We're talking about the unseen physics of machining. Okay, let's dive into this. When you pop the hood of a high-performance vehicle like a Corvette, you see these incredibly clean, shiny, perfectly fitted metal parts, right? The engine block, the pistons, the brake rotors, it all looks so incredibly precise and, honestly, almost peaceful. But getting solid metal to look and function exactly like this, well, it requires what can only be described as extreme 1100-degree thermodynamic violence. We're talking about physically ripping solid metal apart at a microscopic level just to make our modern world run. Take a close look at this forged crankshaft here. See those perfectly shiny, smooth bearing surfaces right in the middle? When metal parts are first created, by pouring molten liquid into a sand cast or just pounding it out in a forge, they actually come out incredibly rough. Basic casting or forming simply cannot achieve the level of precision and smoothness we need for high-speed, moving parts to work together. If you put a roughly cast crankshaft into a car engine, the friction would literally tear it apart in seconds. So, to get this gleaming finish, we have no choice but to aggressively cut the solid metal.
So what exactly is machining? Well, by definition, machining is the removal of material and the modification of workpiece surfaces after they've been initially shaped. It's fundamentally a subtractive process. We aren't molding the metal here like clay. We're deliberately cutting it, scraping it, and removing it to achieve the exact final net shape needed for a mechanical part to function perfectly out in the real world. And we absolutely have to do this because of the strict limitations of those initial shaping processes. Machining is mandatory if we want closer dimensional accuracy. Sometimes we're chasing tolerances down to tiny fractions of a millimeter. We also need it to create sharp geometric features, precision threaded holes so bolts can actually hold the car together, and really specific surface textures that might be needed to retain engine oil or reflect light. To get high-performance parts, we basically have to get a little aggressive with the metal.
Section 1. The physics of the cut. A microscopic reality. When we hear the word cutting, we almost always picture slicing a piece of paper with scissors or cleanly chopping a carrot in the kitchen. But cutting industrial metal? It's not like that at all. Instead of a clean slice, I want you to think about taking a rigid, sharp knife and slowly scraping it along the top of a cold stick of butter. You aren't slicing through the butter. You're pushing against the surface until the butter yields, bulges up, and slides off in a continuous curl. That's exactly what's happening to solid metal. Step 1. The tool pushes into the material. Step 2. Extreme plastic deformation occurs. And Step 3. The material physically yields and shears off in a highly localized zone that engineers call the shear plane. And this brilliantly illustrates that exact concept in action. This is the high-speed shearing of industrial metal. That cutting tool on the right is plunging into the spinning metal cylinder on the left. It's definitely not slicing delicately, is it? It's aggressively pushing, forcing the metal to yield and shear off right at that microscopic plane, which generates massive amounts of force and friction. You can literally see the metal chips flying away from the deformation zone.
Section 2. Anatomy of a metal chip. Let's look closer at those flying pieces.
Those little metal curls aren't just factory trash. They're essentially a microscopic diary. They tell the entire, detailed story of the physics, the friction, and the forces at play during the exact moment of the cut. Check out these two extreme examples under the microscope. On the left, we have a continuous chip. This happens with ductile, softer materials. The shear plane is steady, and the metal flows off the cutting tool in this long, smooth ribbon. But on the right, look at that jagged sawtooth structure. That's a serrated chip. This happens with really tough metals that have low thermal conductivity, like titanium. The metal actually heats up and softens in violent localized bursts, creating this highly segmented, jagged chip due to what we call shear localization.
And sometimes the physics get even weirder. There's this fascinating phenomenon called a built-up edge, or BUE. The friction and pressure at the tip of the cutting tool gets so incredibly intense that layers of the metal workpiece literally weld themselves right onto the cutting tool. It's like the tool puts on a microscopic helmet made of the material it's trying to cut. And because of work hardening, this built-up edge can be up to 3 times harder than the bulk metal itself. It constantly builds up and breaks off, effectively changing the geometry of the tool and completely ruining the smooth finish of the part if it isn't controlled properly by adjusting your speed or lubrication.
Section 3. Dealing with the heat. We've talked friction, now we need to talk temperature.
Now, what's really interesting about this slide is the sheer scale of the thermodynamics happening here. Look at this staggering number, 1100 degrees Celsius. At the exact microscopic interface where the tool pushes against the metal, all that energy from plastic deformation and friction converts directly into heat. In high-speed machining of tough steels, the local temperature can soar to 1100 degrees. That's hot enough to turn the metal chips glowing red hot, creating a literal fire hazard as they fly off the machine. But here's the absolute wild part, the real engineering miracle. 90%. Despite generating temperatures that can melt lesser metals and permanently deform industrial cutting tools, the tool doesn't just instantly disintegrate. Why? Because 90% of that intense heat is actually carried away by the flying chip itself. The chip acts like a sponge, absorbing the thermal energy and evacuating it from the cutting zone in milliseconds. So the chip is acting as your primary heat sink, taking 90% of the thermal load, leaving only about 10% to be absorbed by the cutting tool and the workpiece. What's even more fascinating is that as you increase the cutting speed, an even larger proportion of the total heat generated goes right into the chip. This is exactly why manufacturing engineers are constantly pushing for higher and higher cutting speeds. They want that chip to fly away with the heat before it even has a chance to soak into the cutting tool and destroy it.
Section 4. The ultimate compromise. The tool life trade-off. Because speed always comes with a cost.
This right here is the eternal battle mechanical engineers face every single day on the factory floor, trying to balance time, money, and physics. It all boils down to this deceptively simple math equation formulated way back in the 1890s by F.W. Taylor, V times T to the power of N equals C. Now don't worry, we're not going to do heavy algebra today, but here's what you absolutely need to know. V is your cutting speed, T is your tool life, meaning how long the tool lasts before it wears out or just snaps. They are mathematically locked in a harsh tug of war. For any given material, if V goes up, T violently goes down. So the crucial point is how this plays out in reality. Let's say you're cutting cast iron. At a conservative cutting speed of 60 meters per minute, your tool lasts a respectable 40 minutes. But your factory manager comes over and says, hey, we need to make parts faster to meet demand. So you double the machine speed to 120 meters per minute. Your tool life doesn't just get cut in half, it completely falls off a cliff, dropping to a mere 5 minutes. Doubling your speed literally obliterated your tool life.
And this isn't just an abstract math problem, right? This is a very expensive, everyday reality. If you speed up production to make parts fast, you generate incredibly high heat, and you suffer a rapid tool death. That means you have to constantly stop the machines to replace expensive cutting inserts, wiping out any of the time you just saved. But on the flip side, if you run the machine slowly just to save your tools, your overall production plummets, causing unprofitable delays. It is a massive, high-stakes balancing act between maximizing material removal and minimizing tool replacement.
Which leaves us with the ultimate question. Where is that perfect economic sweet spot between making parts fast and burning through expensive tools? Every single car, airplane, and smartphone around you is the result of engineers constantly walking this mathematical tightrope. Next time you look at a perfectly machined piece of metal, I really hope you appreciate the microscopic violence and the precise mathematical compromises it took to bring it to you. Thanks for joining me on this explainer, and keep questioning how the world around you is built.